In today's note, we're going to look at bonding between elements or different atoms. So we're basically going to look at how certain compounds are formed and how to classify some of the compounds. So just as a reminder, from our past notes, we've learned that atoms are neutral when they have an equal number of protons and electrons. Atoms can form ions when they have a different number of protons and electrons, so when there's a different number, they're no longer neutral. We have to remember that cations or positive ions means that there's more protons than electrons because we have a positive charge, and anions are negative ions, which means there are more electrons in the atom, because those negative charges overpower the positive ones. And we should remember again that most metals form cations or positive ions, and most nonmetals form anions or negative ions. So when combining atoms want to combine to become more stable. And again, remember that the charges they want to have a full outer valence electron shell to be stable. So a lot of times they're going to combine to help that. So atoms can become more stable by gaining, losing, or sharing electrons. We've talked about gaining and losing electrons in the formation of ions in our previous notes, but sharing electrons is something new, and we'll touch on that today. Again, the goal for atoms is to have a full valence shell or the full outer shell, whether it is that duet rule or that octet rule of having either 8 in its outer shell or 2 in its outer shell, depending on which element it is. So when combining atoms, there are kind of 3 different cases that we can look at. We can look at metals and metals, metals and nonmetals, and nonmetals combining. So we're going to focus primarily on the metals and nonmetals, and the metals and nonmetals, and the nonmetals and metals combining. Looking at metals and metals though, they do form mixtures called alloys. So we can combine 2 metals together. We're basically going to form a mixture called an alloy. And it's created by melting 2 or more metals together. So we're not really chemically combining them. We're more or less melting them and mixing them together. And then when they solidify, they form a new metal. So because of this, alloys are not considered compounds. Compounds are when atoms or the atoms of different elements are joined chemically, but in the case of alloys, they are not. They're considered solutions. And if we remember back to our early notes, a solution is a combination of different parts or different molecules where you can't tell the difference. And basically the reason that we kind of create alloys is or combine metals in general is to gain different properties, or to give properties, or to combine the properties of certain metals. So this is just an example of some of the common alloys out there. So we have brass, which is a combination of copper and zinc, bronze, which is a combination of copper and tin, rose gold, which is gold and copper, solder, which is lead and tin. So again, these all have common uses in our everyday lives, but they don't exist as a single element. They are a compound or an alloy, or so a combination of 2 elements. We also have sterling silver, which is silver and copper. We have white gold, which is a combination of gold, palladium, nickel, and zinc. And we have Woods gold, which is bismuth, lead, tin, and cadmium. So again, there's many more alloys out there. These are just some of them. I'm sure you've heard of some of them already. So combining metals and nonmetals. So metals and nonmetals form ionic compounds with ionic bonds. So this is specific to metals and nonmetals. Again, we want to remember that metals lose electrons to become positive, and nonmetals gain electrons to become negative. So those positive and negative ions, or the cations and the anions, they attract to each other due to their opposite charges. So the negative charges on the anions are attracted to the positive charges on the cations. So you can think of kind of 2 ends of a magnet, the positive end and the negative end. They're attracted to each other. It's the same in this scenario with the positive and negative charges of the ions. So these are some examples of ionic compounds. Sodium chloride, so we have a metal and a nonmetal, which is your basic table salt. Potassium chloride, again a metal and a nonmetal, and they form potash, which is a fertilizer. And then we have magnesium and hydroxide, which forms to make milk of magnesia, which is an antacid that you would drink to kind of cure like stomach acid or acid reflux, stuff like that. Again, different from alloys, you can tell just based on the appearance, but we do see, looking at the atomic or the chemical formula, that it is a non-metal and a metal combined together. Looking at nonmetals and nonmetals, so when nonmetals combine, they do not lose or gain electrons. Right? We talked about with the ionic compounds, the cations and the anions, the metals would lose electrons and the nonmetals would gain electrons. However, when we're dealing with two nonmetals or multiple nonmetals, they do not lose or gain electrons. What happens though is that they share electrons between atoms, or they form what is called a covalent bond. So basically, the attraction between the nucleus and the electrons it's too strong to break. So one atom is not going to pull the electron away from the other. So what they end up doing is they end up sharing the electron between the atoms to get a stable or a full outer shell. And again, this bond or this sharing of electrons is a covalent bond. So basically these two electrons are shared, or two electrons are shared in one bond between two atoms. So this is an example of what we mean by sharing of atoms. So if we look here, we can see the hydrogen atom, we can see another hydrogen atom, and a oxygen atom. So hydrogen is a nonmetal, so it can react with other nonmetals and they can share electrons. So oxygen isn't strong enough to pull the electron away from hydrogen, and hydrogen isn't strong enough to pull an electron away from oxygen. But what will happen is that they'll get close enough where they overlap so that their electrons are shared. So oxygen now has a total of 8, and each hydrogen has a total of 2, which is all that it requires. Another example would be ammonia, same idea, right? Nitrogen and hydrogen, so two nonmetals, they're sharing electrons because neither has enough energy or enough attractive forces to pull the electrons away from the other element or the other atom, so they're going to share. So nitrogen now has a total of 8, 2 on its own, and then it's sharing, and it's sharing. So it's forming 3 bonds with 1 hydrogen each. Hydrogen now has 2 electrons in its outer shell because of that bond that is formed with ammonia. So again, just a more visual example of what we mean by the electrons being shared. So some examples of or covalent compounds or metals or nonmetals and nonmetals. We have sucrose, which is a combination of carbon, hydrogen, and oxygen, and basically that's sugar. We have acetylsalic acid or aspirin, which is again another combination of carbon, hydrogen, and oxygen. And we have ammonia, which we saw chemically on the last slide, which is the main ingredient in a lot of cleaning solutions such as Windex. Again, we saw water in the other slide as well, which is a covalent compound or 2 nonmetals combined together. What we're going to look at now is drawing the compounds. We're going to represent them and show how they're formed. And we're going to do that by drawing Lewis dot diagrams. So Lewis dot diagrams are a variation of the Bohr-Rutherford diagrams. They're a little bit easier and they're more specifically used for when we're drawing compounds. So like I said, they are similar to the Bohr-Rutherford diagrams that we've drawn in the past. However, what they require is they only include the element symbol and the electrons in the valence shell. So they only require the electrons that are in the outermost shell. They don't care about the shells that are full, such as the first shell, so the 2 and then the 8 and so on. They're only worried about how many electrons are in the outermost shell. So what we're going to do, again, like I said before, we're only really focusing on the first 20 in this course. So we're just going to draw the Lewis diagrams for the first 20 elements. Again, we only want to have the electrons shown that are in the valence the valence shell, so in that outer shell. So hydrogen only has 1 in its outer shell. Helium has 2. Lithium has 1. Beryllium has 2. Boron has 3. Calcium, or it's not calcium, carbon has 4. Nitrogen has 5. Oxygen has 6. Fluorine has 7. Neon has 8. And again, I'm just going to go through and fill them out. But you can start, as I fill them out, at least try to look and see if you can see a pattern between the number of electrons in the valence shell. There should be one pattern that comes up, and it will be helpful to remember this pattern. That way we don't have to worry about drawing Bohr diagrams the entire time and then having to you go right into the Lewis diagrams. If we can recognize the pattern of the electrons in the valence shell, it makes it a lot easier to just jump right into the Lewis dot diagrams, especially when we're dealing with compounds. But Lewis dot diagrams tend to be a lot easier to draw because we don't have to worry about writing in the protons and the neutrons and writing in all the different shells and representing them. But this is what our periodic table would look like for the first 20 if they were only Lewis dot diagrams. And the pattern that you should see is that each group has the same number of electrons in its valence shell. And I believe we touched on that when we looked at some of the chemical families. But again, just another representation of it. The group that the element is in determines the number of electrons in the valence shell. So we have group 1 and group 2 on our left. So these have two. So group 1 has 1 electron in its valence shell. Group 2 has 2 electrons in its valence shell. All these metals here, the transition metals, we tend not to worry about them because, and you'll learn in further grades that these, they don't really fit the pattern in terms of how many electrons they lose or they gain. So we tend to skip over these, go right to the 13th column. So 13, or you could think of 3. There's going to be 3 electrons, 14, 4, 5, 6, 7, and 8. Again, the odd one is up here, helium. Just remember that helium is an odd one because it only has 2 electrons in its outer shell. But you can think of if an element has 8, or that 18th group are the noble gases, and its outer shell is always full. So helium has an outer shell of 2 because it only has 2 electrons, but it is still full compared to all the other ones which have 8. So again, that's just an easy way to remember to help you draw the Lewis diagrams. So to draw a compound, or to represent the creation of a compound, for our ionic diagrams, we want to remember, again, we're dealing with a metal and a non-metal. The metal loses the electron, the non-metal gains the electron. So if we look at calcium, calcium has, again, we talked about it, it has 2 electrons in its outer shell, or in its valence shell, and oxygen has 6 in its outer shell. So if we're adding these two together, again, we want to remember that calcium, being a nonmetal, wants to lose electrons. So it's going to lose 1 electron, and it's going to lose a second electron to oxygen. And oxygen wants to gain 2 electrons, so it's convenient so that it can gain the 2 electrons that calcium wants to give up. So that's how we show that the electrons are being given to oxygen, and then we're going to draw the ions. So we have calcium, its outer shell is now full, so it has a charge of 2 plus. And then we have oxygen, its outer shell is now full with 8, and we have a charge of 2 minus. So that would be how we represent the compound of calcium and oxygen, or calcium oxide. So we just use the Lewis dot diagram to represent the transfer of ions, and then we write out our ions below, or next. Let's try another example with lithium and sulfur. So sulfur has, we want to again draw, we know there's going to be, if it's Li2, there's going to be 2 lithium, and there's going to be 1 sulfur. So again, we need to then write out the Lewis dot diagrams. So sulfur is in the same case as oxygen. It will have 6 electrons in its outer shell. 6 electrons in its outer shell, and lithium has 1 electron in its outer shell. So in this case, lithium only has 1 electron to give up, so it's going to give up 1 to sulfur, but again, it doesn't there's not enough in that 1 lithium to complete the outer shell, or the valence shell of sulfur. So we need to have there would need to be another lithium atom that joins with sulfur to give it another electron. So that's why we require 2 lithiums. Again, if you weren't sure of that, if you only had the 1 lithium there, you would realize that sulfur is still not full, so we would need to add in another one. So what that yields is we have lithium, 1 lithium atom with a charge of 1 or plus 1. We have our sulfur atom with a charge of 2 minus, and we can draw in our other lithium ion as well, because it's joined with the sulfur and has a charge of 1 plus. So that would be our representation of lithium sulfur. When we're drawing covalent compounds where we're dealing only with nonmetals, this one's a little different because electrons are shared between atoms, so we represent it a little differently. And because the electrons are shared, we have covalent bonds that are forming, and we use a straight line to represent the covalent bonds. So we're still going to start off the same. We're going to look at carbon. Carbon has 4 valence electrons. Oxygen has 6 valence electrons. And again, remember that carbon, or in CO2, so carbon and oxygen are 2 nonmetals, so they're going to share electrons. So if I were to look at carbon and hydrogen, they're going to share these 2 electrons. So they're going to form 1 bond. Make it a little bit nicer. So they're going to form 1 bond. So Carbon right now would technically then have 5 electrons. Oxygen would have 7. They're also going to form another bond, or they're going to share these two. So that means oxygen is now full, but carbon still has 2 remaining electrons. So we would have to add in another oxygen atom, which is part of why our chemical formula requires 2 oxygen atoms. And in these 2 oxygen atoms, or in this second oxygen atom, it's going to share or create a bond with the 2 remaining carbon atoms. So now carbon has a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons. Even though they're shared with oxygen, they still are a part of carbon. And oxygen has its 4 electrons on its own, and it's sharing 4 with carbon, so it has a total of 8. And same with the other oxygen atom. So each atom is full, it's shared, it's full, it has 8 electrons, even though it's shared. And now we're going to draw what the compound would look like. So this is going to be a little different, and the way we draw these is we're going to start off with our oxygen atom. We're going to draw a line to represent the sharing. So this line, or these 2 lines here, represent 4 electrons in total. So the 2 sets of 2 on oxygen plus the 2 bonds gives it a total of 8. Carbon, and it's sharing 2 electrons, or it's forming 2 bonds with another oxygen, which has a total of 8 as well. So looking at it, it may look a little bit complicated, but oxygen has 2 electrons and 2 electrons, 2 electrons in the one bond, 2 electrons in the other bond, for a total of 8. Carbon has 2 electrons, 2, 2, 2, 2, and 2 to create 8, all in the bonds, all being shared, and the other oxygen on the other side is the exact same. So it has 2 electrons, 2 electrons that are on its own, and then 4 that are combined in the sharing or in the covalent bonds. So that's how we'd represent CO2. Looking at carbon and hydrogen, so looking at the chemical formula CH4, we know that we're going to have 1 carbon and 4 hydrogen. So I'm going to draw my 1 carbon atom using the Lewis dot diagrams. And if I didn't know that it required 4 hydrogen, I could just start off with 1. So if I start off with 1 hydrogen with its 1 electron in its outer shell, because they're 2 nonmetals, they're going to share that. So now hydrogen is full, however carbon is not. Carbon still requires 3 more electrons to be shared with it. So if that's the case, I'm going to need to draw 3 more hydrogens for a total of 4. So if you're using the chemical formula, it's very easy to tell how many you have. But if you don't have it, just start off with 1. If you don't have all the electrons, or the 8 electrons or 2 electrons for each atom, then you may have to add in extra ones. So we can see that each hydrogen only has 2 electrons. The carbon in the center has 4 bonds, so it has 8 total electrons. So these atoms are balanced, or they have a full outer shell or valence shell, so they are complete. So if we're going to draw this, so we have our carbon in the middle, and it's forming a covalent bond with each hydrogen. So there are 2 electrons in each line, carbon has a total of 8, and each hydrogen has a total of 2, so both of those are complete. So that is our representation of CH4. The other thing that we could be drawing is diatomic molecules, and basically diatomic molecules, they kind of come from the name, so it's just basically two atoms of the same element that join. These are not considered compounds because there's only one element, so these are just considered elements. Right? It just tends to be that this is the way that these elements are found in nature. Right? They're found usually joined together, and they always tend to form a gas. So O2, or oxygen gas, basically means we have two oxygen atoms. So we have O and O. They both have 6 electrons in their outer shell. Because they're two nonmetals, they're not going to lose electrons to each other or gain electrons from each other. So what's going to happen is they're going to share electrons. So they're going to share electrons. So they're going to form two bonds. By forming the two bonds, they are full. They have 8 electrons in their outer shells, and we can represent that. So there's oxygen, and it's forming two bonds with another oxygen, and in total they both have 8 electrons in their outer shell, so they are good. Nitrogen gas, same idea. N2, so I have nitrogen, which has 5 electrons in its outer shell, and then I have another nitrogen that has 5 electrons in its outer shell, and this element wants to again share electrons. We have two nonmetals together, so they're going to share electrons. So these two are going to share, and then we get a little bit complicated, but then those ones are going to share. So we're going to have actually a triple bond between these two nitrogens, and they're going to share 3 sets for a total of 8 in total. So that means we have nitrogen with its 2 electrons on its own, forming a triple bond with the other nitrogen, and they're both completely full because they have 8 electrons in total, 6 that are shared between them, and then there are 2 other ones on its own. So again, just as a summary, remember alloys are a metal and a metal. You're not really forming an actual compound because you're just melting them. You're not combining them chemically. Ionic compounds are a metal and a nonmetal. And again, electrons are gained and electrons are lost. So you have a cation and an anion combining because of the opposite charges, and ionic bonds are formed. With covalent compounds, you have a nonmetal and a nonmetal. And in this case, because you have two nonmetals, the electrons are shared between them, and in that sharing, covalent bonds are formed. So again, the key things are the 3 different types of compounds, how they're formed, and how we can draw them or represent them using the Lewis dot diagrams.